We're back, and today we're going to talk a little bit about heat, something which I could use a lot of right now since this classroom is freezing. Just remember heat, first off, energy gets transformed from a higher concentration, which we call a source, to a lower concentration, which is called a sink. And in this apparatus here, which you'll be doing a lab on coming up, we have some foam cups. There's an aluminum bar connecting the two cups, and in each cup is water, one being hot, the other is cold. And there's thermometers to measure the temperature in each cup. And this is what I mean by heat transfer, energy transfer. It's not going to go from any cold cup to the hot cup. There's no such thing as like the cold energy transferring over. It's going to go from hot to cold, from source to sink. Now this direction is almost always a one-way street, unless we use outside energy. Think of refrigerators and air conditioners, which can use, you plug them into the wall and they use outside energy to actually remove heat, which is why your freezer is cold and your air conditioner is cold. All right, another term to remember, dynamic equilibrium. We've talked about this earlier in the year. This occurs whenever energy is balanced, the word equilibrium. So heat gained equals heat lost, and temperature remains the same. This is what thermostats do inside of a home. They maintain your home's temperature at a dynamic equilibrium. If the temperature drops below a certain amount, it kicks the furnace on, and that boosts the heat up inside the house, and once it reaches that happy temperature that the thermometer set at, it will shut the heat off and keep doing that. Just like your body has a thermostat to keep it at roughly 98.6 degrees Fahrenheit. If it gets too hot, you start to sweat. If you get too cold, you start to shiver. All right, the methods of heat transfer. There's three we're going to learn, and they start off with conduction. This is the transfer of heat through solid contact. Kind of like the frying pan is a solid touching the solid stove underneath it, the burner, and cooking some sausages, it looks like here, touching the solid surface of the pan. So direct contact with a solid, that's conduction. It also happens right where the air molecules touch the hot pavement in the daytime. And you can see the infrared radiation coming off there is kind of distorting the image. But I'm not talking about the air way above the surface, but right at the surface. That air is heated by conduction as well. Conduction, heat transferred by vibrations of the aluminum molecules in the bar. And this is like that lab we're going to do. The hot water is heating up that aluminum bar, and it's transferring its energy to the cold cup. And that's that solid bar is what's doing it. Okay, the next method of heat transfer, not with solids, but with liquids and gases, and that's convection. We've talked a lot about convection in this course so far. Circular movements of air and sea breezes, magma in the asthenosphere. You can see in this photograph here, hot air density waves convecting upwards in the direction of that red arrow. And the hot air is rising just inches away from the sideways facing hot plate. And there's convection in magma inside the earth. The reason why it's rising, you guys should know this by now, is the density of those hotter materials is less than the material surrounding them, and so they are pushed upwards. And we also did quite a bit with breezes. The warm air rises, moves out over the colder ocean and sinks in the daytime, and it reverses in nighttime, all due to density differences. And this also produces, thermals in the daytime, where hot surfaces, the air rises, and cooler surfaces, the air is going to sink. All right, the last method of heat transfer, radiation. This method occurs through solids, liquids, gases, and also the vacuum of outer space. Good example here, we got sunlight warming up the blacktop parking lot. That's radiation. Or heating up your Pop-Tart in the microwave oven. That's also radiation using microwaves. And this, and hopefully I'm going to be showing you a demonstration of something just like this, shows how a radiometer is receiving radiation and therefore moving direct radiation from that heat source. Earth absorbs shortwave radiation and emits long-wave radiation, and you really, really, really have to know this. In this picture over here, you can see the sunlight coming in as shortwave visible light, and also in ultraviolet radiation, which you can't see. And when it heats up the sand here, it's going to re-radiate it, or radiate it off as long-wave radiation, infrared radiation, and that's heat. So there's different types. And all three methods summed up in one picture here. We have our conduction with the handle heating up the person's hand right there, solid contact. We have our convection occurring in the liquids and also in some of the hot air above it. And we have radiation, which is coming right off of this flame in all directions. So convection, conduction, and radiation. Now they all play a part in something called Earth's energy budget. And this is an interesting diagram to look at, because what we have here is 100% incoming solar energy, 100%. And some of that energy doesn't make it to the Earth's surface. It's reflected by the Earth's atmosphere, by clouds, by the Earth's surface. And if you add up these numbers, you get 30%. That means 70% is reaching the Earth's surface. Now, if you add up these numbers over here, the energy coming off the Earth, that's also 70%. But what would happen if energy in versus energy out were not in balance? Now, I want you to think about that question. Think about that question real hard, because if it's not balanced, something's going to change. And later on in this unit, we're going to get more into that particular question, but just keep that in mind. And that's it for today, guys. See you next time.